I'm Mansi, and I want to welcome you to another exciting episode of Climate Stack. We're going to flip the conversation today and not talk about how software is being applied to climate action, but talk about the impact of our software industry on the climate itself.
This is Joshua. I'm really intrigued about our conversation today. We have the pleasure of having Charles Humble joining us from the United Kingdom. Charles is a freelance consultant, author, and podcaster himself. A former CTO turned highly decorated tech journalist, he has held the editor-in-chief title at publications like InfoQ and Container Solutions. One of his primary areas of interest is how we as engineers can make our own craft more sustainable. Charles, why don't we start with your career story first as a way of getting to know you? What do you do right now, and how did you get there?
Okay, let's go all the way back to the very beginning. I think it's the easiest way to do that. So I graduated with a degree in English literature in about 1994. And my first job was actually in publishing. And I didn't like it all that much, to be honest. I wasn't very good at it. But I've been lucky enough to have access to a BBC Model B computer at school. So the BBC Model B was an 8-bit computer. We're talking about 1982, I think. So I would have been about 10 years old. So that was the first thing I ever programmed in, and I got sufficiently into it that my parents, bless them, about a year later, bought me a Commodore 64. And one of the things that really excited me about the Commodore 64 was I could write music on it, and that was really exciting. And so I got really quite good at programming because I got really interested in programming music, and that in turn meant I had to learn how to write assembly code. So I got pretty nerdy, pretty young. So when I graduated with an English literature degree, I got a job in publishing, as I said. I didn't like it very much. But then I found quite quickly that they had sort of problems that I could solve with writing bits of automation code. So we had, Visual Basic and Microsoft Access and things like that lying around. And I would write little bits of code to solve problems. And I started thinking, well, maybe I should make my career in IT instead of publishing. That seems like a plan. So I got a job in desktop support. I did that for a while, and I gradually made my way up over the course of about, 20 years. So, programmer, senior programmer, architect, and then eventually a CTO. And I did the CTO thing at a couple of startups, one of which got acquired. And after the acquisition went through, and I did a year for a sort of very large consulting firm, I then thought, I really want to do something else. And I got a job for a company called C4 Media as chief editor of a huge programming website called InfoQ. And I was there for about 6 years as chief editor at InfoQ, and also involved quite heavily in the QCon conferences. So I did that for about 6 years, and then I joined a cloud consultancy firm called Container Solutions. I was with Container Solutions for about 3 years, again as an editor. And I'm now working as a freelancer, doing quite a lot of sort of tech advisory type work for very small companies, doing a bit of fairly nascent advice around sustainability and that sort of thing. So I'm kind of an IT journalist, but from a very technical background rather than from a journalism background, if that makes sense.
No, it really does. And I can see that being really valuable to get more deeply into these issues. So the next question I'd like to ask is really obvious, but I'd still love to hear your views on it. Why do you care about climate change, and what attracted you to climate change over the journey you just described?
I think that's an obvious question. Actually, I think that's a great question. So here's the thing. I was speaking at an event last week, and someone came up to me and said, aren't you just advocating for us all to go back to the Stone Age? And I'm absolutely not doing that. I believe very firmly that climate change is something that, yes, we need to solve it, but actually I think we can solve it without necessarily needing to make enormous sacrifices. I'm very pragmatic about a lot of this stuff. And what's interesting is we've tackled a lot of it already. So about the same time as getting interested in computers, I was also getting interested in climate change. And we don't talk about it much anymore, but the number one climate-related thing when I was growing up was acid rain, which is caused by sulfur dioxide, which is a gas that gets produced when we burn coal. And I was about 7 or 8, I guess, when I first heard about it. And I'll be honest, I didn't really understand it. I was terrified. Apart from anything else, I knew what acid was. And, I thought, God, will it melt me if I go out in it? And how will I know? Because it looks like rain and, all of that. Well, it turns out it doesn't melt people, fairly obviously, so that's good. But it does terrible things to ecosystems. It dissolves sculptures, it strips forests of their leaves, it leaches into the soil and leaches out nutrients and pollutes rivers and lakes. And generally, it's very bad. It also pays no attention whatsoever to borders. So, emissions from the US would blow over to Canada, emissions from the UK, where I'm from, would blow over to places like Sweden and Norway. And that was bad enough that it would cause like major diplomatic incidents. It was a big, big deal. So you might be thinking, well, why don't we hear about acid rain anymore? And the answer is we solved it. So what happened was governments signed terribly clunky seeming international agreements. Those international agreements placed limits on power plants in terms of coal burning, and so they started to reduce coal burning. And those interventions were incredibly effective. So in Europe, sulfur dioxide emissions fell by about 84%. In the US, it's about 90%. In the UK, it's about 98%. And the point I think about this is it's a demonstration of the fact that if we want to, this is stuff that we can solve. We just have to really want to do it. Funnily enough, we did much the same thing with the ozone hole, if you remember the ozone hole. I think it's very easy when you start thinking about climate change in any sort of detail to fall into a kind of doom loop and just think, well, this is terrible and there's nothing we can do, and so we'll do nothing. But I don't think that's right. I actually feel very strongly that we can solve this stuff if we want to. The other thing, specifically with my IT hat on, is the IT industry is a major contributor to a particular problem, which is the problem of greenhouse gases. And it is relatively easy for us as an industry to clean up. And so we can fix this problem. And as an industry, we can do stuff that, much faster than other industries can.
That's actually a very inspiring way of looking at this problem. Especially the acid rain example really gives me hope. But talking about software industry in particular, I have actually heard you on another podcast, The New Stack, where you did a fantastic job of explaining how software industry can reduce their emissions. But I feel this chain of thought from software to emissions, it's not always very obvious. So to break this down for our listeners, how about we first start and talk about energy or the power industry and its emissions, and then we will bring in the power-hungry compute workloads that are using up all of this carbon-emitting power.
So thank you, first of all. It's very kind of you to say. The thing with the energy transition, so moving on from acid rain, the next issue that we have is greenhouse gases. There are a number of greenhouse gases that include things like methane and nitrous oxide and hydrofluorocarbons, those sorts of things. But the one that we need to be thinking about as our industry is carbon dioxide. And that's mostly caused by burning fossil fuels, so things like coal and oil and natural gas, to produce electricity. And as an industry, we use a lot of electricity, which means we're a major contributor to the problem. In terms of how major a contributor we are, data center consumption grows fairly modestly, or has done historically, but still, the 2021 data would be somewhere between like 220 and 320 terawatt hours just for data center electricity consumption alone. If you add data transmission networks in, you can add about another 250 to 340 terawatt hours. So for a bit of context, that's roughly the amount of electricity that a country like Brazil burns through. And we get away with that as an industry because we're a lot less visible, and therefore we're less of a poster child for climate change than say, aviation is or farming is. But as I was saying, even though it's not necessarily straightforward, it is easier for us to address the bulk of our emissions than it is for an industry like farming. So the key with acid rain was that the cost of installing scrubbers was significant but not budget breaking, which meant that countries, they felt compelled to act because there was legislation that meant they had to, but they also felt able to act. It was a reasonable thing to do. With lower carbon technologies, it's sort of the same path. So lower carbon technologies used to be incredibly expensive, but over the last decade or so, the price of solar energy has fallen by about 90%, I think. The price of wind energy is about 70%. Battery costs have also fallen dramatically, and the tech is getting better. So solar panels are getting dramatically more efficient. So we're getting to a point where we can generate more of our electricity from renewable sources than we were able to before. If you throw nuclear into that mix, then we absolutely 100% can generate the electricity we need from renewable sources, from green sources, should we say. That's the good news. The bad news is that there's a whole thing to do with balancing the grid, which is complicated. But the short version of it is we can't rely on 100% always on electricity all the time during the transition. My view is in the end, we'll get to a point where once again we can. But in the meantime, we will have periods of time where our electricity supply is less reliable than we're used to. And so again, coming back to what we need to do as an industry, that means things like designing systems so that if a service isn't available, we can still return results to a user, that kind of thing. Now, because we shifted largely to distributed systems anyway, so microservices and things, we're actually quite good at that already. It's just this is another factor that we need to weigh in as a planet, we start shifting away from fossil fuels for electricity use. Again, just to be clear about it, I'm not against electricity. I think electricity is great. I'm just against fossil fuels. That's my point. So what we want to be doing is we want to be generating as much electricity as we can from renewables and from nuclear. And I do think nuclear has to be part of the mix and not from oil and gas. Basically, that's it. So that's where the energy transition thing comes in.
I'm really happy to hear you say nuclear. I know it's contentious, but I really enjoyed the line Stuart Brand took on it in his last book. Yes, it's a problem. We've got other problems too. So, we need to consult all the opportunities. And there's a whole conversation there that maybe we'll have sometime. I want to go back to something you said about electricity being unreliable during the transition. Do you really think that I have a hard time feeling that people will tolerate electricity being unreliable? To a lot of people, that is the kind of end of the world or great suffering that you were talking about.
The reason that it happens is, or the reason that I think it will happen more, is because, as I was saying, balancing the grid is really difficult. So demand for electricity changes through the day and supply always needs to meet that demand. And the difficult job of maintaining that service reliably typically falls to the national grid in a country. So that's responsible for trying to balance the amount of electricity that's being delivered against the amount of electricity that's being consumed. National grids need the ability to stop and start power generation really at a moment's notice for that purpose. And that's much easier to achieve with fossil fuels because fossil fuels have ready supply. So if your electricity suddenly rises, you can burn more coal and have more electricity really fast. And conversely, if your demand falls, you can stop burning coal and that amount of electricity you're generating falls really quickly. There's a term for that, which is the dispatchability of power generation. In the case of renewables, like wind and solar, they're less controllable. So you can't control the weather, much as you might want to. What that means is sometimes you have to throw away renewable electricity because there's too much of it, and you're trying to avoid a blackout on the network. What that all means is that shifting to renewables is going to be more complicated. And as I said, I think nuclear is part of the solution to this. It is very controversial in green circles, as I'm sure you know, but I think it has to be part of the mixture. But yeah, my guess is, as I say, while we are transitioning, our electricity may be less reliable than we're used to for a period.
That's interesting. So it's almost like thinking of electricity as another constraint to our software architecture, or rather, availability of renewable electricity as a software constraint. Like you said, we've already gotten really good at writing software that is resilient to failures and have built sophisticated microservices over the years that are burstable, geographically redistributable, and in most cases have the ability to fail over for continued uptime. So thinking of moving non-critical workloads, at least the workloads that aren't latency sensitive, to use more and more renewable power is an extremely powerful idea. How do you suppose people should think about architecting software for renewables?
So there's a general point there, I guess, which is that, as I was saying, we've got better at, because microservices are distributed and distributed systems are inherently unreliable, we've got better at making them resilient. And as an example of that, something like graceful degradation. So if you are Netflix and you're trying to fetch your list of movie recommendations or something, and you can't reach the movie recommendation service, you'll go and pull that from a cache and display it to the user. And the movie recommendations might be a couple of days old or something, but that doesn't really matter that much. The user probably doesn't notice. And with microservices service systems in general, we've got quite good at that. So we've got quite good at, I can't reach service X, but I can use this thing instead. We can do exactly the same thing with carbon. So we can do a cache discard and recreate the results at the point when the grid is greenest, and in the meantime just show you slightly stale results for an awful lot of things, and that's fine. So it's really just a matter of thinking of having carbon intensity, if you like, as another factor that you weigh into the results that you're generating, or the processing you're doing, and trying to think about, are there things that I can be doing that allow me to recreate my results in a greener, in a more carbon sustainable way, rather than always assuming that I can do them in real time all the time. There's a bunch of stuff that the big cloud providers offer, like burstable instances, but also spot instances that have a lot of qualities that apply in a very similar kind of way. So like spot instances are ephemeral, they can disappear at any moment. They're also green for interesting reasons, or greener, and really cheap. So it might be that you can do a bunch of stuff on spot instances, save yourself a bunch of money, but you do have to keep in mind that, your spot instance might disappear. So your software needs to be aware of that. The reason they're greener, by the way, has a lot to do with something called energy proportionality, which is, it's basically that the computers get more efficient the more work they do. So if you have a computer sitting around doing not very much, it still burns quite a lot of electricity. So if you can bin pack your server and run, use multi-tenanting and stuff to run more workloads on it, then it will get more and more efficient in terms of the amount of useful work it's doing relative to the electricity it's burning, up to about 80%. Over provisioning, which we all used to do and probably still all do, is not good. So, right sizing is a really good thing to do. Auto sizing is a really good thing to do, so long as you scale down as well as scaling up, all of those kind of things. But thinking about how can I get more of my workload how can I get more running on one individual machine is a really good thing to be doing.
And how about AI? How is the AI gold rush changing things on the workload front?
Okay, so with the AI stuff, getting actual data on this is quite tricky because, as you said, we're kind of in the middle of a gold rush, particularly with generative AI, large language models and so on. So there is a lot of secrecy. So as an example, if you go and read the ChatGPT 4 paper from OpenAI, it basically doesn't tell you anything about model size, about parameters, about electricity use and so forth. The GPT-3 paper, on the other hand, does tell you a little bit. So it says that, large-scale pre-training requires large amounts of computation, as you would guess, and is energy intensive. No surprises there. It also says that they consume several thousand petaflop days of compute during pre-training. If you go and read the GPT-2 paper, the GPT-2 model took about, tens of petaflop days. So we've gone from tens to several thousand between 2 and 3. I would assume that the step from 3 to 4 is a similar, several orders of magnitude more. I don't know that because they don't tell us. They won't tell us. But I would assume that's probably true. It's quite bad. It's not, I'll be honest, it's not as bad as I thought it would be before I read the papers. But it is quite bad. So there's a separate research paper that estimated that GPT-3 probably used about 1,287 gigawatt hours and generated about 502 tons of carbon. So that's about 120 years worth of a single US family's electricity use, roughly. Some other estimates have put it a lot higher. The thing that's frustrating about this from a training point of view is training isn't latency sensitive. So you 100% could do all of your training on renewable energy. You absolutely could do that. It would just take a bit longer. The downside at the moment is that's a trade-off that we're not prepared to make. But I kind of feel that it's a trade-off that we should be prepared to make. It's also worth saying, though, that the training cost isn't necessarily the bad bit. So training is incredibly expensive, but then if you have a successful model, you're then running that in production for probably years and years and years. And actually, the cost of running it in production is probably more than the training cost. And at that point, all of the same things you would do for any other kind of workload apply in much the same way. So there's nothing else. There's one other thing we should probably throw into that mixture, though, which is what we call embodied carbon. So embodied carbon is the carbon that's used to create and destroy hardware, essentially. And for end-user devices, so things like your mobile phone, the embodied carbon is much higher than the carbon that gets used to charge the thing for its life. So what that means is, specifically for your mobile phone, what you really want to do is keep it as long as possible. So find one where the company that makes it supports it for a long time and hang on to it for as long as you possibly can. Same deal with your laptop. The EU has advice on this, and their advice is you should keep your mobile phone for 10 years. which I'll wager is about 2 to 3 times more probably than you keep your phone at the moment. But that's the sort of general, that's about the point that it pays out. With data centers, it's a bit different. So funnily enough, with data centers, most of the carbon that gets emitted is actually emitted from using carbon for electricity purposes rather than from the manufacture. But obviously there is embodied carbon there as well. With GPUs, there's this really interesting question that we don't have the answer to yet, which is obviously constructing a lot of GPU compute is burning through an awful lot of carbon. When we finish training our large language models, what do we do with all of those GPUs? Unless you've got lots of matrices to multiply, they're not very useful for anything else. Unless you're on video, in which case you probably don't care that much. But for the rest of us, this is interesting thing. There's all of this very specialized compute is going to be sitting around, and we probably need to find uses for it. I'm not sure what those uses would be.
Well, I'm sure we'll keep finding better uses for these GPUs. I don't think we've run out of all the cat filters we can build so far. But all of this is a lot to digest, right? There is the embodied carbon, the electricity that is being used to run our workloads, and the carbon footprint of that electricity, and whether it's being provided through renewable sources or not. So, as a developer, as a person who's writing software code, what tools or levers do I have to be able to sort of tell the energy intensity, the carbon intensity for the piece of software that I am writing?
I can certainly try. The short and not very good answer is it's actually quite hard. Again, this is quite nascent tech, so a lot of the tech is not that brilliant. Most of the big cloud providers have tools you can use. So AWS has the AWS carbon footprint tool, for example, which you can use to assess your carbon footprint on their particular platform. And as I say, most of the cloud providers offer that. There is an open source tool called the Cloud Carbon Footprint Tool. It's sponsored by ThoughtWorks, and that can measure and monitor and reduce your carbon emissions on public clouds. The Green Software Foundation, who we haven't mentioned, but they're brilliant, they're an offshoot of the Linux Foundation. They do really good work, and they have a formula for calculating carbon intensity. I'm not going to try and go through the formula on a podcast because I'd need a whiteboard. But what it shows is basically you want to use less electricity and use less physical resources to perform the same function. What it also shows is that location matters because different regions have a different mixture of energy. And what that means is that a really quick win for a lot of us is just to look at the energy mix of the different regions that we run our workloads on and pick the green ones. So a tool like Electricity Maps, they've partnered with Google and AWS and Salesforce and can provide customers with real-time global coverage of the carbon intensity of electricity, and that's brilliant. But even like super basically, go on there, have a look at the different regions that your particular cloud provider offers and pick the one with the greenest mix. You're already doing a good thing, even if you can't necessarily measure it yet. There are APIs available, so there's Watt Time, that's Watt as in W-A-T-T rather than the other spelling, and the GSF has a carbon-aware SDK, and with those you can apply some more advanced techniques. So you can do something called demand shifting, which is basically responding to shifts in carbon intensity by increasing or decreasing your demand. And that might be based on location. So you might move workloads around hemispheres depending on the season, for example. So, to areas where there are more sunlight. It might also be time-based, so sort of batching workloads to run, when it's sunnier or windier, and therefore the carbon intensity is lower. So those are some of the main things. We've talked about one or two of the other ideas. It's worth saying as well, though, that you do tend to have to use proxies quite a lot. So you can't always get reliable carbon data, but there are things that you can do, like basically if you're lowering your cloud bill and reducing your cost, you are probably burning less carbon. I say probably because there are some limitations with that. Your cloud providers don't necessarily factor carbon awareness into your bill. And electricity cost isn't necessarily linked to the greenness of its production. But in general, if you lower the costs of your cloud bill rather, if you lower your cloud bill, then you are probably lowering your carbon emissions as well. Which again is why things like right sizing is a really good thing to do. Just Holly Cunnings from Red Hat has this wonderful thing she called light switch ops, which is the idea that you should be able to turn your servers on and off when you're not using them, in the same way you turn a light on and off. So if you've got test machines, say, or QA environments or something like that, do you need them on at weekends? Do you need them on in the evenings? If you don't, switch them off. Obviously, you need to be able to switch them back on again, which requires a bit of work, but just doing that can be dramatic. The other thing is to run audits. So it's quite common when you move stuff from one data center to another to do an audit and discover that, 50% of your computers are actually not doing anything useful or something like that. There's all of these applications running, but no one's used in years. So get into the habit of just doing an audit occasionally. Zombies are bad, so let's kill them. And it turns out that we quite often, if you've been running for any length of time, you quite often have a lot of those kind of things. So I would say, even if you're not yet in a position to measure your carbon reliably, looking at things like cost, doing audits on what am I running and do I need to be running it, all of those sorts of things, you will already be doing good work, even if you're not in a position yet to measure. And as I say, beyond that, the cloud providers have good tooling. There are some open source options and so on.
I'm going to ask you what I hope is a softball for you, but for me, it's something I genuinely wrestle with. And you touched on it when you said that we already have a proxy for our carbon consumption, and that's cost. And that's along the way I've thought of it. And I've also observed that we do care about cost, and we do our best to reduce it in all the ways you're talking about. But there are always competing pressures in the software industry. And you said earlier also, latency isn't an issue for training a model. And it isn't from an engineering perspective, but it is from a business perspective. Because if it takes me twice as long to train my model and my competitor is done and seizes the news cycle or releases a product or just advances their own work, I'm losing. And that same fiduciary responsibility falls down to us as system administrators, as directors, in deciding how much resource to put toward decreasing cost. And it's already valuable to decrease costs. I tend to feel that in the absence of legislation or electricity costs going up, I won't have the discretion or the fiduciary ability to put that much resource into reducing my usage. And in a world where people demand that they can eat pineapple in the middle of winter, how do you get people to do the right thing? But your light switch example, that gives me a little hope. Acid rain example, the acid rain really turned on legislation. So anyway, I think you see what I'm asking.
And you're absolutely right. So I think that this will require legislation in some form as well. I think there will need to be legislation because I think there will need to be a bit of a playing field leveler happening somewhere to encourage us and other industries to do the right thing. As it happens, that's already happening, at least in Europe. So Europe already has what they call a CBAM, which is essentially carbon tax. So it's a tax on goods being sold in and out of the EU based on carbon, the carbon emissions. It's new and it's coming in over the next sort of few years. I think IT has about 8 or 9 years before it's affected by it, but I think it will be affected by it. But there's an interesting thing here as well, which is that so Bill Gates, ex-Microsoft guy, wrote a really good book. You probably knew that, right? Wrote a really good book called How to Avoid a Climate Change Disaster. And it's a book that everyone should read. But in that, he talks about he calls it the green premium, I think. It's basically the cost that it takes to go green. What's interesting for us as an industry is a lot of that doesn't apply because green electricity is generally cheaper, which is why lowering your cost is a decent proxy. I think the opposite thing will also happen, by the way. I think that governments will, in the end, have to apply carbon taxes, which means that electricity that comes off non-renewable sources will get more expensive. And my guess would be that will get to a point where it's no longer, even, like a calculation. There are other arguments that you can use depending on your company and your particular circumstances. One thing about being green is that an awful lot of people like it. And so if you're thinking about recruiting really good engineering talent, for example, then being able to say this is a thing that we care about and factor in might be a good recruiting tool, depending on your particular circumstances and environment. It might be really good for your customers as well. So like Apple, as an example, They play privacy really hard. They play sustainability really hard as well. And the reason they do that is, partly because I think they genuinely do care about it as a company, but also because they know it sells them a lot of iPhones. So sometimes you can use those kind of levers as well. I tend to think cost is probably the easiest one to pull on because that's the language your CFO speaks. But there are other levers you can pull on. And you're right, there are trade-offs. I just think it's not unreasonable to have carbon in there as one of your trade-offs. So if you think about machine learning or AI, whatever, as an example of that, I don't think it's unreasonable for you if you're planning on training a new large language model, to pick an example. One question is why? Is your circumstance so different from the circumstances that led us to ChatGPT and Claude and all of the other large language models that you actually need to train a new large language model from scratch? My guess is maybe not for an awful lot of use cases. The other thing is generative AI sufficiently useful as a society that it's worth it? Because if the answer to that question is no, why are you doing it at all? I think there are places where AI absolutely probably is worth it. I think, some of the older deep learning work that was done with protein folding and those sorts of things, absolutely worth the cost. But I am an IT journalist, so obviously I do have skin in this particular game. But I absolutely am not convinced that generative AI is worth the cost. Maybe it is, but I'm not persuaded. But I'm absolutely not persuaded that you necessarily need to go and train a new large language model every single time. If you have better data on a smaller data set, you might actually get better results anyway. But yeah, it is hard. All of these things are trade-offs. It's the same as everything in business and everything always is. I think my plea in general is just let's have the environmental cost of what we do as another thing that we consider along with the other things that we consider.
I just had a quick comment on this. Yes, cost is one factor, but if you look at California and what's happening now, we are having all the big companies go through ESG audit and ESG reporting, which means they have to do reporting on their scope 1, scope 2, scope 3 emissions. And we're not going to get into the details of what that means, but basically, the emissions from your large language model training are actually going to get reported, and there is an implication on that. So that right there could add to your fiduciary duty to do the right thing, even if it costs the same. Choosing a better region to run and choosing a better time of the day to run could have immediate implications.
Yes, and I think as individuals as well, we have a part that we can play in that. So you should absolutely, if you're making big use of a resource, whether that's public cloud or something else, you should be looking at the sustainability story and asking the supplier to tell you about their sustainability story and their ESG scores and whatever else they are. Most, if you think about the big cloud providers as an example, they will respond to pressure from their customers. So, one of the reasons that AWS got very into being green all of a sudden was because their customers were asking them to do it. And, that's what they were responding to. If you want to use ChatGPT, go and ask OpenAI for their sustainability story. And if they can't give you that sustainability story, have a look for a large language model that can. Those sorts of things are comparatively easy to do, I think. With some caution, I'd say, some caution because being an open source maintainer is generally a thankless task. But I think you can do the same thing with open source projects, right? I don't think it's unreasonable. If the big open source project is big enough, I don't think it's unreasonable enough to go along and say, have you thought about sustainability? What does that look like in your world? And, maybe, can I help? It's not, if the open source project is tiny, it's probably not worth it. But if it's like Spring or Kubernetes or something, it absolutely is worth it. I do think we'll have a mixture of regulation and, individual and corporate action probably. But it's also interesting, we've come a long way. I don't think people realize how much better this is than it was 10 years ago. We've already made surprising progress, even though it can sometimes feel, in the current political climate particularly, it can sometimes feel like, this is something that nobody's taking very seriously. But actually, if you scratch under the surface, it turns out there's a lot of really good work being done still. So I think we can be optimistic.
On that optimistic note, flipping the coin on AI a little bit, could we discuss what are the good things here? How is AI helping the situation? And is there a silver lining?
Is there a silver lining? There might be. It's a little hard to know. There are. So we talked a little bit about how balancing the grid is really complicated and how adding renewables into the mix makes that more complicated. That's basically a complicated maths problem. And machine learning is really good at complicated maths problems. So one example, there are quite a lot of research projects running where they're looking at using machine learning algorithms basically to make the calculations and predictions that enable you to balance the grid as balancing the grid gets more complicated. I think that's an area where there are real grounds for optimism. I think there's really good research going on in there. Early results look really, really positive. We've also seen quite a lot of the utility companies have started integrating AI into some other critical operations. One really good example is inspecting and managing the physical infrastructure, so transmission lines, transformers, those kind of things. As an example, overgrown trees are a big cause of blackouts because branches fall on electricity wires to spark fires and so forth. Manual inspection takes time. It's really slow. And the more transmission lines you have, the more, you're talking months and months and months of work. So I know, for example, PG&E in the States, which covers Northern and Central California, have been using machine learning to accelerate those inspections. So basically what they're doing is they're putting drones and helicopters up and taking photographs and then using machine learning models to identify areas that require trimming of trees or pinpoint where faulty equipment is, that kind of thing. There's a bunch of other work that's going on in this area. There's a lot of excitement actually in the electricity industry in general about some of the things that machine learning and AI might be able to do. It is, like all of these things, it's really nascent, so it's really hard to know for sure. But yeah, I think AI probably has a role to play, a positive role to play in some of that stuff. So yeah, I think it could be, I think it could be part of a solution.
You mentioned protein folding, but direct science in general is someplace that I'm really astonished by the research assistant duties they can perform. I mean, LLM synthesis, but I also mean just material science in general. The things, if you're watching the research, just how quickly it's coming out, it's noticeably different. I want to toss in also, you talked about grid optimization, but there's local usage optimization. I think, this is the Jevons paradox. If you're familiar with that term, it's not even a paradox. It's just an observation about human nature that when something becomes cheap, we don't continue to use it as efficiently as we did. We use it less efficiently because it's cheap. I think if you apply that in reverse, as electricity hopefully gets more expensive, we've been so profligate. We leave the lights on, figuratively speaking, in every room in our enormous planetary house. And there's so much slack to take out of that system. And that's another optimization problem that I see machine learning actually being useful for. And I see piles of companies researching that right now, how they can help industry and consumers at a consumer level use less electricity, which people might start thinking about.
There's also things like we were talking about. Well, we've avoided talking about the storage problem. So we've carefully skipped slightly over the whole business of storing electricity, but basically batteries. And doing that at scale is really tricky. Doing that locally is less tricky. So as an example, if you're driving an EV, you've got an enormous battery on wheels sitting in a garage doing nothing for large chunks of the time. Could that be a battery that powers your house some of the time? Probably. There's a bunch of stuff that you need to know about and understand to make that work. Again, I think that might be another place where you see machine learning coming in and being effective. Knowing when you drive and when you don't drive, knowing how far you drive, knowing when to charge the car and when not to, in much the same way you've seen with things like Windows Update will update your Windows at times when the electricity is greenest. And I think you'll see similar kinds of things with things like EVs and batteries in general. That I think that's going to be really hard to do at scale at the moment. But I think local optimizations along those kind of lines is another thing that we'll see. And I think machine learning is part of that too, probably.
Well, I think that this has been really fantastic. Is there anything else that you'd like to share with our listeners? Anything specifically maybe you thought we were going to ask you, but we didn't, or anything you wish we had?
We've done well, I think. We've covered a lot of ground. I am going to plug there's a book by Anne Curry and Sarah Sue and Sarah Bergman called Building Green Software, which has come out on O'Reilly in the last month or two. It's a really good book. I will admit that Anne Curry is a friend, but I'm not plugging it for that reason. I'm plugging it because I've read it twice, and it's very concise and does a really, really good job of covering a lot of the stuff we've talked about and a lot more in a really, really good way. So that's definitely a good plan. If you want an optimistic climate book, then Hannah Ritchie's book, Bill Gates's book, which we mentioned, is really good too. But beyond that, I'll tell you, I've got one other thing. If you are doing good work in this area, go and talk about it. Because one of the things that we're desperately short of is people speaking at conferences, writing on the New Stack or InfoQ or whatever about like real world case studies of good work. And we all, as an industry, learn from each other. But for some reason, we're not talking about this very much yet. So if your company is doing really, even if you feel, oh, it's not that advanced, it's not that good, I bet it's more advanced than most people, because no one, like everyone's at the starting grid at the moment. So if you're making good uses of spot instances and burstable instances, and I don't know, you've got some reasonably accurate indication of your scope 1 and 2 carbon or whatever it is, or scope 2 and 3 probably, go and talk about that, because that's how we'll know and that's how we'll learn. And, other people can learn from your experiences and maybe not repeat some of the mistakes you've made. So, yeah, I think my big plea with all of this now really is, do the individual things, put pressure on your cloud provider or whatever, all good stuff, but also go out and talk about what you're doing and share your knowledge with everybody else.
Charles, thank you for being with us. This conversation has been so eye-opening, even for me, and I knew a lot of it already. I hope that, though it might be a bit controversial, like Josh says, that what is my fiduciary duty when it comes to saving money and being competitive versus doing good for the planet? I hope the conversation has opened the thought process for a few people to think about how these two can come hand in hand and how we can actually not compromise one while doing the other and do good on both ends. Thank you so much.
It's a pleasure. Thank you very much for having me, both of you. Been absolute joy.
Thank you for listening to Climate Stack. If you enjoyed the show, or if there are climate topics or specific companies you'd love for us to cover, please let Monsi or I know on our website or on LinkedIn. Before I go, I also want to thank the Climate Base Fellowship. Climate Base is a climate career accelerator designed to help ambitious, mission-driven professionals supercharge their careers in climate. Monsi and I met and formed the idea for this podcast on Climate Base, and they're taking applications now for their 6th cohort at www.climatebase.org.